Come with the weak shit, I break it. Step into my zone, mad rhymes will stifle ya.
And welcome to the video on curvature. So what is curvature? So, just telling from the word, this is actually kind of self-explanatory as far as the overall definition. It is basically and literally how curvy or bendy, you could consider it bendy, like a bendy straw, how curvy or bendy something is. I guess a curve, you could say. A curve is. Okay? So how much it bends. How much does it bend at a certain point? Okay? How much it bends. Alright, so basically, the way that we measure curvature, let's start with, okay, so here's a curve, alright? And let's say this is our r of t, okay? So it's pointing here. This is r of t arrow, right? And then let's say that our tangent vector, our r prime of t is going in this direction, okay? So this is r prime of t, alright? So this is, that's our tangent vector that we've learned about before, and it's tangent to the curve at a given point, right? And now what we're going to learn is called the unit tangent vector. Unit tangent vector. Vector. And this is usually denoted by a capital T, okay? So capital T is the unit tangent. And what this is basically you take the tangent vector that we already know of, so r prime of t, and what we're going to do is normalize it. So that just means divide by its magnitude, okay? So that means what this does, remember how we normalize things? We make it into unit vectors, right? So this is basically a unit vector, and what this actually is also, you could write it as our velocity vector, because that's what's on top, and on the bottom is our speed function, right? Which is a scalar valued function, not a vector one. Okay, so what we did, again, was normalize this and made our unit tangent actually a unit vector, so of length 1. Alright, so what this should tell us is that a change in the direction of capital T, our unit tangent vector, so a change in this, change in this shows that the path is bending, right? Shows a bit, that, I'll just say that the path is bending, okay? Path is bending. So if you consider it like, if you're comparing this curve, the one that I drew, with something more or less like that, which is a line, our tangent vector would actually be on the line, first of all, and it wouldn't change at all, right? So that's kind of a good contrast there. This is not curvy at all, a line is not, but this is, so this is going to change as you go along, right? So then the tangent vector is going to be here, and it probably was even here at one point, okay? But we do have a problem, because normally, like logically, we would say that the more quickly our unit tangent vector changes, so the more quickly this changes, we would think that it's only logical to think that the curvier the path, right? So if that's changing more quickly, then the path must be curvier. It must be bending more, right? But there's a little bit of a problem here. So if we were to take the magnitude of the change of our unit tangent, so that's what that means, the magnitude of the change in our unit tangent vector, this equals the same thing as d capital T over dt, right? So that's the same thing there. So this is the magnitude, so it's telling us how much of a change. It's not necessarily saying like whether it's negative or positive or anything like that, but it just tells us how much of a change there is. But the problem here is that what we're doing is deriving this with respect to t, okay? And the problem with that is that this makes it, this depends on what? On how fast you're traversing the curve, on how fast you're moving, right? So I'll just put traverse. How fast you traverse or travel along the curve, or the path. You could think of it curve or path. Okay, so that means that if you're moving faster, then t is obviously going to change more quickly. Then t changes more quickly. So how are we going to rectify this situation? So what we can do is actually, on the next slide, so we're going to go to plan B, okay, because plan A, it has some faults in it, and they're pretty significant. So plan B is assuming, so we can assume that we walk, or that we traverse the curve. So assume you traverse curve at unit speed. Okay, so this should kind of ring a bell, right? So unit meaning 1, and speed meaning the magnitude of the velocity vector, right? So this means that we use s instead. So this means, I was trying to draw a star there. Okay, this means we use s for arc length as our parameter. So this should also, again, stimulate or like ring a bell for something of arc length parameterization. Remember? So arc length parameterization. This was when we kind of rephrased or we reparameterized something in order for it to have part A, unit speed. So a constant speed of 1. So that means that r prime of s is equal to 1. The magnitude of that is equal to 1, right? And then our arc length parameterization. So that allowed us to have that unit speed, and along with that we used s as our parameter variable. So that's our arc length parameter. Okay. So what we're going to do is actually from this, instead of having this d capital T dt, instead of having that as our measure, we're going to make it be this instead, dt over ds. Okay, so we're going to take the derivative, or we're going to measure the change based on arc length. So that means like how much of the curve we have traversed over a certain time. Okay, so this is actually going to be our more accurate measure of curvature. Okay, so this is how we denote curvature. All right, so this is curvature. Okay, so the circled thing is what we would like to remember. That's the important thing from this. Okay, and this again, this is for arc length parameterization. Okay, this is the definition of curvature for arc length parameterization. Okay, so let's do an example of measuring curvature, and I kind of alluded to it earlier on in the video. But basically, let's see what the curvature of a line is. So curvature of a line. Okay, so I'll give you guys a line. So let's say we have u is equal to a, b, c. That's our direction vector, okay? And let's say we just have a general line. I'm not going to give any specific numbers because this will hold true for all lines, really. So t times u, this is our direction vector, right? Plus a position vector, just saying like where we're at, where this line goes through. Okay, and that could be 0, 0, 0, or it could be another point. Okay, and then the magnitude of u is equal to 1, all right? So that means that it's already an arc length parameterization, okay? Because then if you were to take, so this part here means arc length parameterization already, because if you take the prime, or take the first derivative of everything, this goes away because those are just numbers. And then the t, that'll just turn into a, b, c, because those are all the coefficients of t, right? And then this, this is equal to the vector u, and then if you take the magnitude of it, then we're just going to get 1. So then we know that r prime of t is equal to 1, because the magnitude of u is equal to 1 as well. Alright, anyways, so the whole deal behind that is to be able to replace our t from this equation here with just an s, right? Because then when you replace it with an s, that means that we're basing it off of, our parameter is the arc length parameter, right? So it's going to depend on the arc length instead of time, which is what we want to measure curvature, right? So anyways, we're going to replace that with an s, and we can do that because I just proved that this was a given, okay? This magnitude of u equals 1, that's a given. So we could just deduce that it's already an arc length parameterization, so you don't really need to do anything to solve for our new arc length parameterization. We just replace it with s, okay, wherever you see a t. So then we have this, right? And now we're just going to kind of expand it out, I guess you could say. So we're going to plug in s times ABC plus x naught, y naught, and z naught. And then I'm going to combine those. So we just get s times a plus x naught. I should write this on the next line. Hold on here. I'll just skip down to the next line there. Okay, so this is going to be equal to s times a plus x naught, comma, s times b plus y naught, and then s times c plus z naught. Okay, so now that we're at this point, this basically just means that I'm going to prove that, I'll continue on the next slide, okay? Just keep this in mind that this is R of S, okay? So, the next step would be saying that R prime of S is equal to, so we're going to pull out the coefficients of S, so that would just be A, B, C, which happens to be the same U vector that we were given in the beginning. And the magnitude of this R prime of S is going to be the magnitude of U, right? And we were also given that that just equals 1. All right. So now, with these two pieces of information, what we can do is construct our tangent vector, our unit tangent vector, that is. So capital T of S now is equal to R prime of S over the magnitude of that R prime of S, okay, for the unit vector. So this is going to equal, R prime of S is equal to U arrow, and then the magnitude is equal to 1, simply. So we just have the U vector here. So this is our unit tangent vector with respect to S, our arc length, right? So now to find curvature, because that's what we're aiming for, so curvature based on arc length is measured by this, dt ds, okay? And this is the same thing as saying the magnitude, yeah, so this is the same as saying the magnitude of T arrow prime of S magnitude, right? Okay, so if we take the magnitude of that, so first of all we have to derive U, okay, so this is the derivative of U, and U is actually just a point, or not a point, but a direction vector. So A, B, and C are all constants. So when we do that, we're just going to get the magnitude of 0, 0, 0, because when you derive, okay, so here, just to go in more in detail, so A, B, C are all constants, so when you derive them, they all turn into zeros. Okay, so that's where I got that from. So this is just going to be curvature for the line is just going to be 0, which is kind of visually logical, right? Because, like as I mentioned before, our tangent vector, they're all pointing in the same direction. So they are unchanging, so that rate of change here that we see, the DDS, that's going to be 0. Okay? Alright, so now we've found out, we've made the discovery, that a line has 0 curvature.
Oh yes, I'm greater than all MCs. When I breeze, give me room please. I be like fascinating when I be updating, cutting off white kids, pulling their trunk.